Hello and welcome to the Trebuchet Project. I'm Parker Ashlock and I'll be walking you through these first few slides. On this project I was helped by Noah Winkler, Robbie Cox, and Alejandro Molestina. Now I'll be talking about specifically the problem definition that we faced. The problem definition for this project was to simply build a trebuchet to launch marbles. Now, a few of our goals here were to launch a 0.02 kilogram marble projectile and launch it with the highest efficiency ratio determined by the equation below. The mass of the marble times the maximum range, all divided by the mass of the counterweight times the vertical drop of said counterweight. Now, some of the restrictions and design specs we faced were probably the most prominent was that we had to fit the whole trebuchet into a 12 by 12 box, as shown in blue here on our initial blueprint. We also had to reassemble our whole trebuchet within 2 minutes of taking it out of that box, as we were allowed to disassemble some of our parts to an extent in order to make it fit the 12 by 12 inch box. Now, in addition to the 12 by 12 inch box we had to fit the trebuchet in, we also had to design a true trebuchet with the following: a counterweight for propulsion, outlined in green on the slide, a throwing arm to launch our projectile, and that's highlighted in blue, and we also need a string connecting from the throwing arm to a pouch that contains our projectile, and that is outlined in yellow. Now, lastly, one of the other restrictions and design specs we faced was 25% of our trebuchet had to be built with either the 3D printer or utilizing the laser cutter, which we did, and we also had to design and build our entire trebuchet from scratch.
When designing our trebuchet, we knew we wanted to take full advantage of our dimensions and make our frames 12 by 12 inches. To keep it as lightweight as possible, we decided to make our frame entirely out of balsa wood originally, with the metal dowel rod connecting the two frames across the top. Each frame was a 45-45-90 triangle that were connected, both horizontal and vertical beams were both 12 inches in length, connected by a diagonal beam measuring 16.97 inches. The only thing connecting the two frames in our original design was the 12-inch metal dowel rod that was meant to hold up the arm. Our design was simple, but we forgot that 25% of the design had to be 3D printed or laser cut, so we reevaluated our design. We considered laser cutting the 12 by 12 inch base to add to the bottom of our trebuchet, but that didn't account for 25% of our design. So we turned to Tinkercad to improve our design. After thinking for a while, we settled on a 3D print design that would help our design reach the requirement. The first 3D print design we made replaced about 2/3 of the balsa wood design. To reach the requirement, we replaced the vertical beam in the two frames with 3D printed filament. We also added in holes at the top of each beam so the dowel rod could pass through at the top. This design seemed to work, but we added to it because we thought the balsa wood would have a hard time gluing directly to the filament. To fix this, we added on hollow rectangles that could fit a 1/4 by 1/4 inch piece of wood snug at the top at a 45-degree angle. We also added on a separate piece made up of 3 of the same hollow rectangles that would go on the bottom of the vertical beam to help reach the height requirement. After designing our entire trebuchet frame, we focused on the sling and pouch. Our first design for this had 2 separate strings going through 2 holes on the arm. The string connected to the pouch at 4 separate corners. We added some duct tape to the edges of the pouch to help keep in the ball during the launch. This design seemed to be inconsistent, so we took our inspiration from other groups and changed to the pin and hook design. First, we nailed a metal pin into the top of our arm, then we restrung the pouch so that there would only be 2 points to connect to. One side of the string was connected to the arm permanently, and the other had a loop tied to it. This design ensured that our trebuchet would launch the ball forward and work how we wanted it to.
We began construction by printing the portion made in Tinkercad. While the print was in process, we found a 12 by 12 piece of wood to act as our base. After the print was completed, we noticed that the tubes placed on the top of our prints had warped and would not fit our 1/4 inch dowel rod, as we had intended. Regardless, we fastened the printed portions to our base, then began cutting lengths of wood to complete the frame for our trebuchet. All wood pieces fit beautifully into our 3D printed molds. While cutting pieces for the frame, we also crafted our arm. We decided to use 4 pieces of 1/4 inch balsa wood glued together to act as our arm. However, we only had 4 pieces thick on the portion of our arm closest to the counterweight, to give our arm more weight and stability. From our research, we knew that the part of the arm extending past the pivot needed to be 1/5 the length of the long arm. So, a 1/4 inch hole was drilled 5 inches from the counterweight to fit the dowel rod. Smaller holes were drilled at the other end for our sling to be attached. Then, the problem concerning the warped dowel rods became our biggest concern. First, we tried warping the tubes so as to fit the rod, but that didn't work. Then we cut the tubes off and decided to replace the plastic with wood. However, during this process, we discovered our height was well above the allocated 12 inches. So, we sanded the vertical plastic prints down by an inch or so to give ourselves plenty of room. Our next idea was to place small wooden cubes with 1/4 inch holes on top of our vertical supports to hold the rod. This was very successful and also made assembly much faster than we anticipated. The largest obstacle our group had to face was the sling, release angle, and design of the pouch. For the majority of our testing, we had two sets of string fastened through our arm without releasing. During our research, we did not realize that we needed part of our sling to release in order to achieve maximum angle and distance. We spent far too long taping and retaping the strings, changing pouch size, and changing inconsequential things about our pouch, hoping to achieve the same results other groups were getting. Finally, on the day before testing, we wised up and stuck a small metal rod into the end of our arm and tied the end of the strings to a metal hole, which would be part of the rod, slipping off mid-flight, giving us a perfect release angle and maximum distance. We also discovered that our sling was getting caught on the edge of our base during launch, so we sanded the edge and added another piece of wood so that the sling would be constantly level with the base.
At first, our trebuchet saw problems with the release mechanism. We tried adjusting the pouch and saw little improvement. In our attempts to launch the marker up, we barely could get the cap to stay in the pouch. Other times the cap would not come out of the pouch. The inconsistency made it really hard to determine the issue. We did some redesign to the pouch and saw some results. We added support to the pouch using duct tape to hold the cap in. At most, the marker cap would launch backwards. We continued resting and assumed the problem was due to the lack of height in the cap. And the marble would be better. More adjustments were made to the pouch for more testing with the marker caps. One adjustment we made was to add an extension to the base to make the launch smoother. We started seeing more consistency and would have more tests go positive distances. At most, the cap would spike into the ground or go straight into the ceiling. We hoped we could get something similar with the marble, considering the marble was much heavier and would probably go further distances. We had good expectations going into the actual testing with the marble on the field. We expected the marble to go forwards on a couple of attempts, and our results were not even close. We may have had the record for most negative distance. After many tests and adjustments, we realized that our pouch needed to be completely redesigned. After the redesign, the pouch release was very consistent. With the marble with many adjustments of the small dowel rod that was used as the pen in the back of our release mechanism, we realized that this could be used to adjust the release angle. Once we reached our perfect 45-degree release angle using slow motion cameras to get the exact release, we reached a maximum distance of 18.5 feet after all of the adjustments. To summarize the progress of testing, the first day we had the results of -5 feet. On day 2 our results were 5 feet. On day 3 our results were 0 feet. And we realized that our launching release was not working. On day 4, after redesign, we reached 18.5 feet. Our final efficiency calculation was 69 feet.